So in conjugated systems, one of the key reactions that we do is Diels-Alder reactions. Okay, these are very, very interesting, very specific reactions. So Diels-Alder, two chemists, okay, they won the Nobel Prize for this reaction because it's a really very, very simple reaction, very neat reaction to do. And also the interesting thing is that it forms a carbon-carbon bond. Okay, and carbon-carbon bond are usually interesting because you need one carbon to be positive, one negative, in order for a reaction to happen. So they're always interesting reactions, okay? So there are a few things that are going on in a Diels-Alder reaction, okay? So first of all, that you have a conjugated diene. You can have more also, but the diene is where we're going to start, okay? So conjugated diene is what you have, and then you have just an alkene. When you react both of these, so this one is a very simple thing. You see there's not a whole lot going on here on the arrow, right? The only thing I can add here is maybe benzene, a solvent, and some heat. Okay, that's it. That's really all that I can add here. There's nothing more required. And then what we end up getting is something like this, okay, which is a cyclic system. So which means you've taken a conjugated system and an alkene and formed something entirely new, a ring system also. Okay, so first of all, very simple reaction. Second of all, so much going on here. So here is the diene. This is called the dienophile, and then this is called the adduct. Okay, so in order for us to understand what is happening in this reaction, because any reaction that we have studied so far has been that, oh, here is a nucleophile, here is an electrophile. But in this, the electrophile and the nucleophile are not clear, okay, because these are all double bonds. So where is my electrophile? Where is my nucleophile? And it turns out that really there is no clear electrophile, nucleophile. All we can say is that the diene is more electron rich, okay, because it has two double bonds. That's it, okay, so it's winning as far as that is concerned. But other than that, there's not a whole lot of other stuff going on, okay, in here. So what I've shown you here with the pink is that those two carbons are right here, okay, for the dienophile. So here's the mechanism for this reaction. This is called a concerted mechanism. A concerted mechanism is where there is no clear beginning or end. So if you were looking at these three arrows, then you're like, which one is the first arrow? Which one should I draw first? And honestly, whichever one you want. So there is no clear ending or beginning for any kind of a concerted mechanism, all right? Because there is no clear electrophile or nucleophile. So you don't have any of that, okay? But anyhow, when you draw the arrows, what you're showing is the formation of the new bonds, okay? So what I've done for you is I've highlighted the new bonds here for you. So this is not a final product. This is not even an intermediate. This is just my way of showing you that, look, here are the new bonds that are being formed. So the highlighted one, the yellow ones, those are the new bonds. So this is completely illegal, okay? I mean, it's possible to form this, but 1, 2, 3, 4, these three double bonds, that's not, that's not what happens at all. So what's happening though is that these electrons are moving here. These electrons in the double bond are moving here to form a new bond. And then these double bonds electrons are moving here to form a new bond. Okay. So if you feel like it and you want to write this out on your own, then the best thing to do is to draw dash lines, okay, like this, and that helps you a little bit, okay? So then you can see, okay, here is the new bond that's formed, here is the new bond that's formed, and of course here is the new bond, right? So that's what I've highlighted here in this middle structure. So the way I look at a Diels-Alder reaction is I look at it as a 2 + 4 system or a 4 + 2 system. How? 4 + 2 system? 1, 2, 3, 4, 1, 2, 3, and 4. So this is the 4 system, and then this is the 2 system. Okay, what is the 2? Again, you need a diene and you need a dienophile. The diene is the 4 electron system, and the dienophile is the 2 electron system. Remember, 2 is the number of electrons in the pi bond. Okay, so in the diene you have 4 pi electrons, in the dienophile you have 2. Okay, so it's a 4 plus 2, and I'm focusing more on where the reaction is taking place. All right, so the 4 plus 2 system then gives you a 6 system, right? And this is not 6 pi, this is giving you a 6 ring system. Okay, so the 4 carbons and the 2 carbons that are important is giving you a 6 carbon structure. So I think of it as a 4 plus 2. So whenever I'm looking at a Diels-Alder reaction, I'm looking at where is my diene, where is my dienophile, where is my 4, 2, 6. Okay, that's kind of what I look for when I'm doing Diels-Alder reactions. So here are some examples. Okay, so here's the dienes written here in the front, and then the second part is the dienophile, and I've colored them so that you can kind of distinguish them in the adduct. Okay, so you can see it's a very straightforward. So it's a 4 plus 2 system. Again, the 4 carbons over here, and then the 2 carbons, which are the pink ones. Okay, so that's kind of, you know, how you draw. Now in this first one's, you're forming one ring, right? Because 4 plus 2 gives you 6. So that's a 6 system. So that's a 6-membered ring you're forming. Now, if you're already starting with a ring here, then you're going to get 2 rings in the end. So this is a bicyclic system. Okay. So hopefully you can see this, okay, of what's going on here. And let me highlight it for you. So this system here, the 5 is this one. Okay, so one of the bonds, this carbon right here, is this pointy one here. Okay, so it's kind of moved up, and this is to accommodate, right, the two carbons that are going to be adding on. So it's to accommodate that. So again, the best thing to do, okay, for these kind of reactions, if you're working on them, when you're working on them, is to identify your 1, 2, 3, 4 system, and then just draw dotted lines, you know, to the 2 system, and then, you know, you have your product. Okay, for so, you know, you'll never be confused when you have a focus for the 4 plus 2, then whether you are forming 2 rings, 3 rings, it's not going to bother you, okay, at that point. So you just join it together. Okay, so we saw the examples, it's all fine, but one thing is still remaining, okay? And the question that's remaining here is, okay, fine, that the diene is electron rich, okay, fine, that dienophile is electron poor, okay, that's what's happening. So, but how does the reaction actually take place, you know? So are these reactions going to be stable? So some of these reactions are actually not stable, okay, so which means that easy to form, easy to break, you know. So sometimes these reactions are not stable, which means that the product is going to decompose. So what can we do in order for these reactions to be, you know, long-term and stable products? Well, if the diene is going to be electron rich, then you can make it even more electron rich. If the dienophile is supposed to be electron poor, you can make it even more electron poor. So what do you do then? You create this imbalance between the diene and the dienophile. So if you create more imbalance, then the bond that's formed is going to be a little bit more stable, because you're not really creating a nucleophile or electrophile, but then you're like, okay, now I can see the electron rich, because that looks then like a nucleophile, but not exactly a nucleophile. Okay, so, you know, you make the diene more electron rich. Essentially, that's what I'm saying. Okay, so let's see how we can make our dienophile and diene better. So for the diene, you need to have electron donating groups. For the dienophile, electron withdrawing groups. So for the dienes, the electron donating groups, these are the electron donating groups, okay? Anything that can push electrons into the system. And how is it pushing electrons? Through the inductive effect, or in cases of alcohols and amines, they actually have lone pair of electrons, okay? And so the lone pair of electrons will then contribute to the conjugation. So even though oxygen, you might think, oh my God, it is electronegative, it pulls electrons, not when it is directly connected to the double bonds, okay? So when it is, then it will actually start conjugation, all right, with it. And so the same thing happens with the amine groups also. Okay, there is direct conjugation. Phenyl groups are generally quite electron rich, so they help to contribute. So again, anything that pushes electrons into the diene is going to be an effective diene. Okay, so now let's look at the electron withdrawing groups. And the electron withdrawing groups in this, if you see, a lot of them, these have carbonyls in them. Now in this case, if you're thinking, oh my God, but you just said oxygen is supposed to be electron donating. Well, in this case, the oxygen is not directly connected to the dienophile. So if it's not directly connected to the dienophile, it is separated by a carbon, then it's going to behave just traditionally like an electron withdrawing group, okay, like an electronegative group. So aldehyde, ketone, acid, ester, amide, all of these are all going to be then electron withdrawing groups. What's not there is something like fluorine, for example, okay, but fluorines generally are quite electronegative, so those will also be good for the dienophile. Okay, so here are some good dienophiles. So you can see how the electronegative groups, can be attached to the dienophiles. So I've given you one here, two groups you can attach to even more, make it more reactive. And then here is a very typical one where you have 3 oxygens, but then this is the diene actually that's doing the reaction. Now I just want to go through some of the characteristics, some of the interesting things about the reaction, because now you know the reaction, how it works, what are the good things about the reaction. So first of all, I want to say that generally when you write a Diels-Alder reaction, you write the diene on the left side and the dienophile on the right side. Okay, nobody says that you have to do this, but it's kind of an unwritten rule, okay, that you do this just for the sanity of it, okay, because it's just easier to visualize. Okay, so that's one thing. Now, the other thing is that what I've done here is I have flipped the dienophile. So I could flip this also, okay, diene, but I'm not flipping this because if I'm flipping this, oh my God, okay, it's just, I don't want to create too much of variations here. So I'm just taking a dienophile, which looks like this, but then I've also flipped it to give you the other side. Okay, I mean, it's just the same thing, right? But if you react the top two, you get this product, this adduct. When you react the bottom two, then you get this one. Now, these two are not the same. You can tell that even just by looking at the relationship of the methyl to the aldehyde. These are not going to be the same compounds. Okay, so what does that mean for us? Does it mean that you're writing 2 products all the time? Does it mean you're flipping? No, you're not flipping. Okay, you're going to keep just the one starting material that we give you. Okay, so which means that if I had not given you this one over here, then you will just write me this product. Okay, that's it. If I gave you this one, then you will give me this product. All right, so just kind of focus on the orientation that is given to you in the question and not try to rotate anything around. Okay, so does it mean you will not get the 2 products? Of course you will get the 2 products, because you can't control molecules. When they're inside a reaction system, they're flipping, they're doing whatever, so yeah, you can get 2 products. So it is up to us to not have those kind of molecules which can give you more products. Okay, it's for us, the designers, to think, okay, this is the synthesis I can do, so I can get 1 product instead of getting 2 products, right? So not have the CHO there maybe, or not have the methyl group there, something like that, okay, to help you to limit the number of products you're going to get. Okay, so that's one of the things I want you to understand. The other thing I want you to understand on this slide is the fact that you can have a triple bond also as a dienophile. Okay, now the nitrile, the CN groups that I have there, I've added the nitrile so you can visualize what's going on, but you don't have to have the nitriles, okay, on there. But what happens when you have a triple bond is that, once you do your reaction, you will still get the double bond here, that's true, but you will still have a double bond remaining, okay, from the triple bond. So now you have two double bonds. So it depends. If you want to have two double bonds like that, then you can use a triple, you can use an alkyne also. Okay, so it's just a different kind of reaction. And the last reaction that I have on this slide shows you that it doesn't have to be a carbon atom here. If you have a heteroatom, that's okay. That heteroatom will also form a ring like this, okay, with the heteroatom right in the ring. Now, most of the times, we stick to the normal kind of 4+2 system. Okay, so generally you don't involve this, but it's possible to do that. Okay, now let's talk just a little bit about stereospecificity in Diels-Alder. What does stereospecificity mean? It means that you have a cis or a trans kind of a starting material. Now, the diene here is the same, right? That's not a problem. But look at the dienophile. Okay, here if you have two groups on the dienophile, those two groups can be either cis or they can be trans. Now, if they are cis, they will give you a cis product. If they are trans, they will give you a trans product. And this is what happens. This is not something you can control. You will get this, and you will also get an enantiomer. Okay, I didn't write the enantiomers, and you don't have to write them for me, but you just have to know that you will get enantiomers also, okay, in there. So this is kind of what happens, okay? So you have to make sure that you show the stereochemistry in case it is given to you in the dienophile. Now let's look at the diene, okay? So the diene also can have different conformations. Now diene is the 4 system, okay, where you have the 4 carbons. So I've given you this diene over here, which is what we have normally seen, okay? So in this case, this is called an S-cis diene. And then if you have the double bonds going in the opposite direction, then this is called the S-trans diene, okay? Now, technically what this is right now, the way I've drawn it, it's fine, but this can easily, remember the single bonds can easily rotate, okay? So this is just to show you what an S-trans would look like, okay? That's all. It's not that this is actually, like this. It's not, okay? It's going to actually, it can rotate around. That's what I'm saying. Okay. So now if you have a cis double bond like this, and again, this is not the double bond per se, like in the 2 hydrogens at the same side. This is S-cis. So when the double bonds are facing on the same side, then that is a preferred type of a conformation versus when the double bonds are on the opposite sides of each other, okay? And the reason for that is about the overlap of orbitals, okay? So now you can see here in the S kind of a system, the overlap is easily possible, okay? I've shown you with the blue line. Now, in the case of where the double bonds are in opposite directions in the trans kind of a system, then the overlap is not possible because some of the orbitals are not in the correct orientation. So when the orientation is not correct, then you cannot have reaction, okay? So the top one is the preferred one, okay? The cis kind of a double bond is preferred. So it means that the double bonds are facing in the same direction. Now, where do you see the trans? The trans, this is not an accurate trans, again, because as I said, the double bond can rotate, okay? So a good trans example is something like this, okay, where you have the double bonds going in the opposite direction, and now the rotation is restricted, okay? This single bond cannot rotate here, okay? So if you had a diene like this one, oh yes, that's the best cyclohexane I've ever drawn. So let's try that again here. So if you had something like this will react, no problem, okay? But because the double bonds are going in opposite directions, this is not really going to react, okay? So that kind of a diene, not a good diene, not preferred for reactions. Another thing about the Diels-Alder reaction is the regioselectivity. Okay, so the regioselectivity is that when you're forming a bicyclic structure, this is not for just a 6 system, okay, this is for a bicyclic structure, then the groups can actually go in 2 different directions, okay? So when these groups, when they attach, okay, when they form an adduct, they can either go down like this, or they can actually go up. like this. So you have an endo product and an exo product. Exo means going towards the bridging carbon over here, and then the endo means going into under the bridge. How is that? Okay, under the roof, you can think of it like that. The endo product is more stable. Why is it more stable? Because there is less steric hindrance here. These two groups can actually interact with the hydrogens on this bridging carbon. Okay, so that means there is less space on the top over here. There is a lot more space here. So the same thing can happen in this case where you're actually forming a tricyclic structure. So again, focus on, I've drawn the lines for you, focus on the 4+2 system. And once you form the ring, there's the ring, this whole ring, this maleic anhydride, it can go down or it can actually go up. Okay, so in both cases, you know, you have in both of these cases you have two products, and the endo is going to be the major product because of less steric hindrance. Okay, so that's another issue that you have with Diels-Alder reactions. Now again, you can reduce some of these issues, you know, and otherwise the major product is endo anyway, right? So major means that you're getting your main product at least. So here is some retrosynthesis for Diels-Alder, because again, you know, retrosynthesis, what do we do without that? So here is a molecule that you need to synthesize. And again, as told you, my focus is always going to be the 4+2 system. What do I do when I see any kind of a structure like this and I'm asked for Diels-Alder? I focus on my double bond. Okay, once I focus on the double bond, then I go ahead and number that 2 and 3 and then number the other 4 system. Then I know I have to break the bonds connecting to 1 and 4. Okay, and that's it. I put the double bonds in the requisite place and then I'm done. Okay, so keeping it simple is what I do. All right, so here again is 2 and 3, the double bond, 2 and 3. The 1 and 2 is over here. Now regarding 1 and 2 over here, that's not 1 and 2. Okay, so be careful. Anyway, and then whenever you have a bicyclic system, it means that at least you have one ring somewhere. Either that ring is coming from the dienophile or it's coming from the diene. Okay, you can figure that out depending on how the bonds are breaking. Okay, in that case. So here, in this case, you know, here's the 2 and 3, which means this is 1, this is 4. So I'll break these two bonds and that's how I get this. Now remember this one here, they are both going in the same direction. So it means my chlorines here have to go in the same direction as well. Okay, and this is then a cyclohexadiene. That's what I'm starting with here. So that's retrosynthesis for Diels-Alder. That's about it. Okay, so just remember how to make a good diene, how to make a good dienophile, some of the stereoselectivity issues, and then retrosynthesis also. Okay.